You know, most AI today are trained to find the single best way to solve a problem. But what happens when that so-called perfect plan hits a snag in the real world? What if that best way is actually a dead end? Well, we're going to dive into some fascinating research that explores a really powerful idea, teaching AI to have not just a plan A, but a whole library of smart backup plans. So, first things first, let's talk about a huge limitation in a lot of AI systems out there. They're often built to just zero in on one single optimal path to get to a goal. And look, that sounds great on paper, but the real world, it's messy, it's unpredictable. And this picture, man, it just nails the whole problem. Imagine you're this little robot ant, right? And your goal is that green block. The most obvious, the best path is straight ahead. But that path leads you right into a wall. It's a trap. An AI that's just laser focused on that one route is going to get stuck, just banging its head against the wall, never figuring out there's a much smarter way to go around. And that's the standard approach. It's called reinforcement learning. Honestly, the best way to think about it is like a GPS that only knows one single route to your destination. On a perfect day with no traffic, it's amazing. But you know what happens next, right? The second there's an accident or road closure, that GPS is totally useless. It has no backup. It's stuck. So this is the crucial point, and the researchers said it perfectly. This single-minded approach is just too fragile. It's brittle. Whether you're talking about a robot trying to get around a warehouse or an AI trying to learn a new skill, relying on just one strategy is basically a recipe for disaster the moment things don't go exactly to plan. So that brings us to what we can call the diversity dilemma. If having just one solution is a no-go, then the big question is, how in the world do you get an AI to find a whole bunch of different, but still really good solutions? How do you teach it to be creative?
Well, the answer comes from this really cool field called quality diversity, or QD for short. The name kind of gives it away, right? The goal isn't just to find the one best answer anymore. It's to build an entire archive of solutions that are both super effective and super different from each other.
Okay, so let's break this down because it's super important. Quality is the part we're all used to. It's just, how good is the solution at its job? We measure that with rewards. But diversity, that's the new exciting secret sauce. It measures how different a solution's behavior is from all the others. Like, is the robot walking, or is it crawling, or maybe it's doing some weird little hop? Those are all different behaviors. Now, the thing is, this isn't a brand new idea, but the early attempts, well, they ran into a hidden problem. They really struggled to find solutions that were great at both quality and diversity. They'd end up with a bunch of options that looked different on a spreadsheet, but in reality, they were all basically doing the same thing. It kind of defeats the purpose, right? All right, so how did this new research crack the code? It all comes down to a really simple but totally brilliant breakthrough in how it chooses which solutions to learn from. Okay, so take a look at these two charts. They really tell the whole story. On the right, you see a plot of quality versus diversity, and those blue dots are the best solutions from the old method. They look pretty spread out, right? Seems good. But then you look at the chart on the left, which shows what the robots are actually doing. And whoa, all those same blue dots are crammed into one tiny little corner. They're not diverse at all. So this old method has a fancy name, Pareto-based selection. But what it was really doing was favoring a big group of solutions that were just slightly different versions of each other. It created this illusion of variety, but they were all behaving in almost the exact same way. The algorithm was basically fooling itself. And this is where the big aha moment comes in. The researchers asked a super simple question. Instead of just picking the solutions with the best-looking scores, what if we first group all of our solutions into different families based on how they actually behave? Think about it like you're picking an all-star team for some crazy obstacle course. You wouldn't just pick the 5 strongest people, right? No way. You'd pick the best swimmer, the best runner, and the best climber. You want a specialist for each type of challenge. And that is exactly what clustering does for the AI. It forces it to find the champion of each different behavior type. And that simple idea gives us this really elegant 3-step process they call EDO-CS. Step 1, cluster. It groups all the solutions by behavior. Step 2, select. It picks the single best solution from inside each of those groups. And step 3, reproduce. It uses that diverse team of champions to create the next generation. It's a simple idea, but it is incredibly powerful. And here we go. This is the after shot. Look at this. The red dots are the solutions picked by this new clustering method. Now look at the behavior space on the left. They are perfectly spread out, with one champion coming from each of the high reward zones. That, right there, is what real diversity looks like in action.
Okay, the theory sounds awesome, right? But the real question is, does it actually work? Let's see what happened when they put this new EDO-CS algorithm to the test in some really tricky simulated robot tasks.
So first up, let's go back to our buddy, the deceptive ant wall. This is that classic AI trap we saw right at the beginning. Can the new algorithm learn to ignore that tempting but totally flawed path and actually discover the smarter route around the wall? Well, the results, they speak for themselves. The standard AI, totally stuck, gets nowhere. In older quality diversity method, it gets there, eventually. But look at EDO-CS. It finds the best way around the wall way faster. It just shows how much better it is at exploring all the possibilities. All right, for the next challenge, they really ramped up the difficulty. It's what's called a multi-modal task. Basically, can you teach one AI to be a master of two completely different things at the same time? In this case, getting a simulated cheetah robot to run both forwards and backwards at peak performance. And again, the numbers are crystal clear. The other methods, they could kind of master one direction, or they were just mediocre at both. But EDO-CS, it crushed it, getting the highest scores for both running forward and running backward. It didn't have to choose. It mastered the whole range of high-quality behaviors. So what's the big picture here? What does all of this mean for where AI and robotics are headed? Well, it hints at a really big shift in how we should think about solving problems. You know, the big idea is so simple. For the really tough, complex problems we face, having more than one good solution isn't just a nice little bonus. It's a massive strategic advantage. It's the difference between an AI that breaks easily and one that's truly resilient. And this is exactly why it matters. This approach creates AI that's just fundamentally more robust. If a robot's leg gets damaged, hey, maybe it has a backup crawling behavior it can just switch to. It's more adaptable. It can tackle new problems by pulling from its whole library of skills. And it's a way better explorer, much less likely to get stuck in a trap like that ant wall, because it's always looking for new, creative ways to get the job done. And that kind of leaves us with a final question to think about. As we build the next generation of intelligent systems, maybe the goal shouldn't be chasing after a single perfect answer. Maybe it should be about creating a rich, deep, and diverse library of really, really good ones. Because in a world that's always throwing curveballs, the most intelligent plan is having a backup plan.